When you're doing hypothesis tests in simple linear regression, there are actually three different ways that people have come up to do the testing. Here's the output from StatCrunch for the weights and tail lengths of the wolves data. Notice that there's a correlation coefficient that we could use. The closer it is to 1 or -1, the more evidence there would be of a significant relationship in a straight line manner. The closer it is to 0, the less evidence of that. You could also look at the equation of the line and ask, is the slope important, right? Could you just get rid of the x variable, not worry about the slope, or does the slope make a difference? And then there's a way to look at all the variability in the data and sort of split it up into what the model sort of accounts for versus what's left over if you don't fit a model, right? And that would give you an F-stat. The null hypothesis essentially indicates that no relationship exists between your two variables x and y, while the alternative indicates that there is some type of linear pattern in the data. And this can be accomplished in different ways. For example, you could write it out in words, right? Weights and tail lengths are not correlated under the null, and under the alternative, weights and tail lengths are correlated. You could put that in sort of your symbolic notation, right? So under the null, R is 0, so the correlation coefficient is 0, versus the alternative says the correlation coefficient R is not 0. You could also write it in terms of your linear model, right? How would you model the data? So under the null, you could say the most appropriate model is just y equals a number and then plus sort of error. Or you could write the alternative that says, no, the model really is best as a line that has a slope to it. So beta sub 0 plus beta 1x. And in this case, beta 1 is representing the value of the slope parameter. So you could see if we put a 0 in there for beta 1, that would make this second term drop off, and we would have just the y equals a number value. Or you could write just focusing on the number for beta 1. If beta 1 is 0 versus the alternative that says beta 1 is non-zero. In other words, x does contribute to the value of y in some way. Now in simple linear regression, where there's only one predictor variable and one response variable, so we have one x and one y, all of these hypotheses and the test statistics you use are basically equivalent. They're just different ways of looking at the same thing. It's sort of like ice and drinking water and steam really are just three manifestations or forms of the same thing, which is water. So the test statistic we could use is the correlation coefficient, right? So that could be the 0.693, or we could use the t-score on the slope row, so the 2.72, or we could use the F statistic from the ANOVA table, 7.3756, or however many digits you want to round it off to. All of these are going to produce the same p-value. In this case, the p-value is 0.0264, no matter where you get it from. Now, you can go into StatCrunch and ask it to give you both the correlation and the p-value associated with that correlation coefficient. But usually what we do is just read that off of the second line in the parameter estimates table. So don't worry about different representations and how to calculate all the different test statistics. Just realize that any of these can be used, and they're all going to there are three ways of calculating information in the data that may support the idea of a linear pattern between your x and y variables. But they're all going to have the same p-value, and you're going to draw the same conclusion no matter the method you use, as long as you're in the type of equation that we're looking at with just one predictor and one response. I think in the iMath homework, the test statistic is asking you for the correlation coefficient, whereas in the set of notes, I presented the t-score from the slope row in the parameter estimates table, and it's just a different perspective. And some people would even teach the F-stat. And if you go on and look at advanced regression models, if you were to take a Stat 316, for example, which is sort of the next class after this one if you wanted to do more regression modeling, then you would start with this, sort of like we did in ANOVA, and then maybe go back and look at t-scores if the F were important. But that's an advanced concept, and that's if you had multiple predictors. When you've got one predictor, these are going to give you the same information because they're representing the same thing when you look at the data. So I just wanted to mention that, and also make sure that you're not confused on any of the homework if it's asking for the correlation coefficient instead of the t-score as the test statistic in the hypothesis test.